This is the class of ECE 350, Principles of Automatic Control. Welcome. Today the class of the Friday of the first week. Right here, we will study the Laplace transform today. Okay. ECE 350, the first week, Friday's class. Okay, for the Laplace transform. Laplace transform. Last time we gave the definition of a Laplace transform, right? Suppose we have a signal x of t, then by the Laplace transform, I put this capital L here, means Laplace transform. We can have capital X of s equal to, it will be a integration from 0 to positive infinite, the given signal x of t times e to negative st dt. Alright, so this is a definition of Laplace transform. And then we know we can use some tables to help us to find the Laplace transform. So let's look at the tables in detail. Last time we used the table to solve one example, right? Now we go over the whole table with more details. Here I have posted the tables in the blackboard. You go to the blackboard, you go to the lecture material, then here I put the tables here. Laplace transform 1, Laplace transform 2, have two forms. Actually they are coming from textbook, you can find them from textbook, yeah. But I put it here, it will be convenience, right? Okay, this which is 2, 2, 3, yeah, this one. We look at this one firstly. Here we have 2 columns, actually 4 columns, but this side and both sides are same thing, right? One columns are the Laplace transform capital F of s. The other columns are time function lowercase f of t. Okay. So they are pairs, they kind of pairs. Then we look at them. The first one is a unit impulse function dirt of t, and its Laplace transform is just 1. Right? Yeah, this one is good, right? It's simple. But what is the dirt of t? What is dirt of t? Let me right here. Here, okay. Dirt t. Dirt t is this one. Its value will be infinite or 0. So either 0, either go to infinite. Here is a t equal to 0. Here is a t to not equal to 0. So its graph looks like here go to infinite. This is the time t, and the original point is here. This is dirt of t. It's here will go to infinite. And we have a restriction on this infinite value. We want the integral of dirt of t from any negative point to positive point. So usually you can just write in this way. This one equal to 1. You know, because you think this is infinite, right? If you times 2 on dirt of t, you times 2 on dirt of t, what will happen? Here 0 times 2 is still 0. Here 2 times infinite, it is still infinite, right? You times 2, if you just look at here, it seems nothing changed. So you want to see 2 times it as same as itself. And that's a weird result, right? 2 times something equal to that one itself. So that is not good. So we add this as a requirement. The integral is 1. If you times 2 on it, the integral will be 2, right? So that will be different. You times 2, it will be double. Okay, So this is delta of t. It's impulse, unit impulse function. Unit impulse function. This is impulse and it's a unit. This is a unit impulse function. Okay, now we go back to the table. Okay, the first one, and then second one, the signal is a unit step function us of t. This we discussed last time, right? This one we discussed last time, and its Laplace transform is 1 over s. Okay, it's fine. The third one is a unit ramp function t. Yeah, t is a ramp, right? T is a ramp. Can I put them together? Okay. Am I good? Alright. Yeah. Now we can see both. T is a unit ramp. Yeah, it looks like this, right? It's T. This is T. Here's a. It's also T, right? It's T. It's T. Yeah. Here's 1. Here will be also 1. Like this. Yeah. This is ramp, right? You need a ramp. The slope is 1. Slope is 1. The straight line. The slope is 1. The unit. And okay. Then for ramp function, this side is 1 over s squared. Yeah. And then t to the n's, the power, n is a positive integer. So the power of t here is also, similar with this one, similar with the first one to now is the third one. This is n factorial over s to the power n plus 1. So this one is a general case for here's a power of t. It include the first order, second order, things like that. First 0 order, the first order. Right? Let me write here. T to the n equal to 0. Tn it is just 1. N equal to 1. Tn it is t. Right? So this case, this is just the us of t. Right? It is just us of t. Us of t is 1. Is 1. Yeah, they are same. These two are same. These two are same for t positive. For p positive. For negative side, they are different. The negative side, this one is all, both sides are 1. Right? This one, us of t. For negative it is 0, but for positive side they are same. And their Laplace transform, this one go to 1 over s, and this one we by this rule, you see, n equal to positive integer. Now n is not just positive, 0 is also fine. This is n 0, t 0, n is 0, that is a 0 factorial t s times 0 plus 1, right? Now n is 0. Here's a 0 factorial times over s to the 0 plus 1, so s to 1, just s, right? So 0 factorial over s. 0 factorial over s. 0 factorial is 1. So this is 1 over s. Same thing, right? Same. So you apply this or apply this? Now you apply the second term, second line, or the fourth line when n is 0, they are same thing. And when n is 1, that is n equal to 0 case. When n is 1, we use these. We will have, by Laplace transform, we have 1 factorial over s 1 plus 1, which is 1 over s squared. You see, as same as second term, third term, right? Third term, as same as third term. So same thing. Yeah. So this fourth one, it is a general case, include the second line and the third line. Yeah. Okay. So these are the 1, 2, 3, 4. Then the fifth, 1 over s plus alpha. This side is e to the negative at. This one we have used it last time, right? I didn't show you how to get it. I just use it. If you are interested, you can read the textbook. It's not hard. Just integral. Then you can have this one. Yeah. Now you can just know how to use the table. That will be fine. Yeah. And the next is here's times t on the e to the negative at, and here's you add a square on it. And then you see we have something in generally t to the nth times e to the negative at, and this side is n factorial over s plus a to the power n plus 1. So similar thing. This one, it is a generalization of the previous two terms. These two terms, one this is e to the negative at, this is t times e to the negative at. They are special case of this one when n is 0 or 1. If you plug 0, n equal to 0 or n equal to 1 here, you will get the previous two results. And furthermore, if alpha is 0, what will happen? Alpha is 0 here, e to the negative rt, there will be 1. And this side, when alpha is 0, it is just s to the power n plus 1. You see here, s to the n plus 1. So this one is for any alpha, and here this is special case when alpha is 0. You see, so you know this one formula contains all the above 1, 2, 3, 4, 5 different cases. You just change the value of the parameter. N could be 0 or 1. Alpha could be 0 or non-zero. Yeah. Yeah. But of course, here we give the function directly here. Then when you use them, that will be very convenient. Right? Okay. Then we have more. Some combination of the exponential powers with certain coefficient, right? different cases, and this side they are something, some 1 over some s plus alpha, s plus beta, or s over or something, where I want to go over them step by step. When you use it, when you have some signal you can find them, then you can try to use them. Right. Similar with last time we used this one, right? Remember? Last time we used this one. Yeah. Okay. And okay, this is one side. The other side, this graph. Can I see? Can I see the other side? Okay. Yeah. This side. This side, the signal. Here are more complex, but in the first 3 lines there are some simple one: sine, cosine, and 1 minus cosine, and so on. Actually, here most common used, we have sine, we have cosine, and that one, that is let me see, this one, this line, this one. This is a exponential power times sine, exponential power times sine, with certain kind of coefficients. And this side is this one is a constant in the numerator, and the denominator is a polynomial on s. The power is the order is 2, and the coefficients looks like this. This one we will use this one a lot later. All right. And the rest of them, you have chance to use them, but I just you know we have some result here. If you want, if it is necessary, you can try to find them. All right. So this is the this is one table. We have another table. Okay. All right. This table gave us some theorems of Laplace transform. they are kind of rules. You know, you use these rules, use these theorems, then you know how to find the Laplace transform or go back from Laplace transform to the time domain. Yeah. The first one is Laplace transform of L time Laplace transform of k times a signal equal to k times f, capital F of s. Okay. Then we can use an example to explain it. How to use them. Actually, for the table we have two features. One feature is why we can have this formula. This one actually you can check the textbook. They give more details. They give all the details, step by step. Why can we have these theorems? All right, this is one side. The other side is how to use them. Right? How to use them. So the first one, what is the meaning of this? How to use them? So here I can think like, suppose like we have f of t equal to 3 times e to the negative 2t. Now what is a Laplace transform? Okay, we have two tables. By this table, we know this. Okay, this one. We know we have e to the negative rt according to 1 over s plus a, right? So we know e to the negative 2t by Laplace transform, we will have 1 over s plus 2. Right? We have this. This is from table. Then now I times 3 on it. Okay, so 3 times e to the negative 2t will go to, you see, here you times 3 and here you still times 3. 3 1 over s plus 2. This one is ft in table. Not this ft. This ft is we use this ft denote the signal. When you look at the table, you use this term in the table. Here you have a f. This f is this part, and this is k. This is k in table. This is k in the table. This is k in the table, and this one, and also this one, they are the capital F of s, and this is k. Right? This is also k. Yeah, now it is clear, right? This one, what is the Laplace transform of these? It is 3 times 1 over s plus 2. Right. Okay, this is one example, right? We use the first one. The second one, this example 1. Second example, I use like x of t equal to 3 times e to negative 2t. I keep this part, and plus 4 times sine of pi over 6t. For example, I have this one. Then what is the Laplace transform of this one? We want to find x of s equal to 1. Okay, then you see we have two part, right? Two part. Each part is 3 times 4 times something. So each part we can have 3e to negative 2t. By Laplace transform, we have this one, right? We already know this one. And 4 times sine pi over 6t. By Laplace transform will be 4 times the similar rule of this part. Now it's a sine. We find the Laplace transform of this part. And this part, we check the table. This table we have sine, right? Remember we have a sine on it. We have sine. Here's a sine omega t. We go to time domain, go to s domain. This one. So this one is omega n. Omega n now is a pi over 6. And s squared plus omega n squared, that is a pi over 6 squared. Okay, so each term we have the Laplace transform. Now is the summation of these two. Alright, now we can apply this one. You see, summation of two functions, perform Laplace transform. You just find the Laplace transform of each one, then do the summation. The subtract will be similar, right? Okay, so now we have capital X of S equal to, the first term is 3 over S plus 2, and second term is 4 times on it. That will be 4 times it. That will be 2 pi over 3, right? Yeah, 4 times pi over 6. I have 2 pi over 3 over S squared plus pi over 6 squared. Alright, so we get this one. So we can apply the second. And the third one, yeah, it's just you should just follow it, apply it. Actually, this part are very useful to solve the equation. We need this property when we try to solve the system, solve the equation, like y3 derivative plus y1 derivative equal to, input is x, so we have a system looks like this. Then we perform Laplace transform. We already have s with 3 times derivative. Then we can use this one. L, here's a Laplace of d to n, dn ft. So this is nth order derivative. So now n is 3. So we plug in here. N is 3. We have s to 3. Now is y of s, right? And minus s to the n is 3. Now is 2. Now y of 0. And minus s, n is 3. 3 minus 2 is 1. So just s. And f, now is y. Y take 1 derivative, 0. And minus, next will be what? The power of s will decrease, right? So s next will be just 1, the power on s. And f now is y. Derivative will increase, right? Here's no derivative. This is 1 derivative. That's a 2 derivative. And here's a 0. Okay, no more, because the last term is a term without s. You see, the last term is a term without s. So here now we already reached the last term, right? This is a term without s. Okay, then equal to, this side is x. X by Laplace transform is capital X of s. So we can have this one. Right. So we will apply these differentiation formulas when we try to solve a system, solve an equation. We can just apply it like this one. Then from here we can have oh, I lost one term, sorry, I forget this one. And plus y prime, just this one is s times y of s minus y of 0. It's here. This part will be here. Alright. Yeah. Then we can try to solve this. Of course, you need the value of this one, and this one. If you do not have these 3 values, you can't solve it. They are the initial value of y, right? Initial value. So when these values are given, you plug in the value here. Then this part, they are given, right? You know them. And y is unknown. This is given value, and x is a given input. Then you can solve. Y is only only unknowns. You can solve it. Right? Okay, so this is the this one, differentiation. All right, and next, integration. Integration is also, you know, when you try to solve a system, you can apply it. For example, we can consider a system with both integration and derivative and integral. We have both, right? Example, okay, this is a example 1, 2. This is a 3, and now is example 4. Like we have a system, for example, we have y2 prime plus 2y plus 3 integral of y. It's t on t run from this. It should be a function, so here 0 to t, 0 to t. So confused. Another y of tau, d tau. It should be t, but I will separate. These two are different, so here I use tau, right? Like this one. Input is r. For example, you have a system looks like this. Can you have these kind of things? Yeah, you need to have it. For example, you have a system with like we have capacity or instructor. Then you have you need an integral, right? You need both, maybe two derivative, maybe some chemical or some mechanical, some different kind of system. Maybe you need this one. You need this one. Yeah. Then how to solve it? This one we know this totally by Laplace transform. We perform Laplace transform on the whole function. Then we have this one is s squared times y of s minus, now it's s is y of 0 minus 1 times y prime of 0, right? The power of s is decreasing, and the derivative here is increase. The first one is y of 0, and plus 2 times y of s, and this one is plus 3 times y of s over s, right? And equal to r of s. Then you see it is also a function with unknown capital Y. Capital Y is unknown. Suppose this is given, and this is given, then you can solve what is a capital Y. Right? Okay, so this is an integration formula. And next is a shift in time. Okay, this function, this theorem is a little bit confused. You can see we perform a shift on f of t, shift to capital T, shift by capital T. And then in the s domain, we still have capital F of s, but we need a multiplier exponential power in front of it. This exponential power is e to the negative capital Ts. This capital T coming from this shift. But the shift is what? Not just the shift f itself. We need times us of t minus capital T. What is this? Okay, so we can look at it here for shift in time. We have f t minus t, and we have f t minus t times us of t. What are these three things? We can think like use an example to explain it. Suppose this is a ft. Then shift by capital T. This is ft minus capital T. This 0 point now go to here. This is t equal to t. Lowercase t equal to capital T. Right? So get this one. This is shifted of f. And what this is times t. Sorry, I lost this part. Right. Same as here. us of t minus capital T. What is this? This is okay. You can see what is this? This is a us of t minus t. This one. This one. Here are zeros. This part u equal to 0. This part u equal to 0. Right? U is this one. This is us of t. This one. Then shift by t. Shift by t. Right? Here's a step. Then the step move to here. the step move to here. Okay, you times this f and u together, you multiply these two together. Here value is 1, right? Here's 1. So when t run in this part, larger than t, right? T time is larger than capital T. This is 1. This is some function value. You times these two together, because this is 1, right? So time together, it is just this part, right? This times 1. So t, here's a t. This part, it is just this. F of t minus capital T times us of t minus capital T. It is just this one. When time t is larger than capital T. And when time is smaller than capital T, in this side, this part, you see, here's 0. So 0 times some value here, you get 0. Alright, you got it? So the shift, the shift f of t, if we just shift itself, we get this one. We will move those part, when t is a negative part, to the positive part. We will move this part to here, right? We will keep that. And if you multiply us of t, this part you will drop down and replace by 0. Replace by 0. Here, when we say shift in time, we need a shifted signal which has this part is 0. Now, this is non-zero, but this is 0. Why we need 0 here? Because the Laplace transform, by definition, here's an integral from 0 to integrations from 0 to infinite. Right? No negative side. The t, we do not want those t equal to negative value. Right? Negative t, for negative time, we don't need it. Here t must be positive, 0 to positive infinity. Right? T run from 0 to positive infinity. So we do not need those parts. When we calculate Laplace transform of f of t, this part we do not need them. Now we shift it to here. When we shift, this part go to here. So if you find the Laplace transform of this one, you will use this part. That result is different with this one. Right? In this case, this part you do not use it, and here you use it. Okay. To avoid this part, times this one, you cut off. You cut off this part, because here's a 0. Right? You think it's, you cut it. You cut it, erase it, remove them. You get this one. Okay. Then you use this one to calculate the Laplace transform, and use this one to calculate the Laplace transform. So for these two, they are closed. They have a closed relation, right? The closed relation is here. Relation is here. Your times. This, of course, they are different. So you need the times this term on it. Yeah, but they have a formula. If you do not have this part, you do not have this us times on it. You will have these. Then the Laplace transform of this one and this one, they do not have a general relation. You cannot give a formula to connect these two together. It's hard because this part, you can imagine now is ft looks like this, right? If ft looks like this, or if ft looks like this, these three cases, for f of t, you perform Laplace transform, you will get same thing, because the negative side doesn't matter what it is, right? You can use different value, you get same thing. But when you shift here, if it is looks like this or looks like this, these three cases, of course, Laplace transform are different, but all of them, they are the shift of this one. You cannot have a general formula for that, right? This part is totally cannot understand, cannot to be determined. It's something we have different kind of possible, right? But this one, there's no doubt, because this part we just read Yeah, then it will be same. Okay, so this is for the shift of this one. Now look at the next. Next is we call it initial value 0. Limit when t go to 0. What is this limit value of f of t? It is when here should be s go to infinity. Okay, s go to infinity. Yeah, typo. S go to infinity. Here's s times f of s. So it's for initial value 0. It is a limit. Here's a t go to 0, f of t equal to limit. Now it's s go to infinity and s times f of s. And it's this one. I can use an example to explain it. I have some signal x in the s domain. X of s equal to, for example, is s over s plus 3. Then as for x of t, when t go to infinity, t tend to infinity, what is this? What is this? Okay, then you can have two ways. The first way is you try to perform inverse Laplace transform, find x of t equal to something, and then plug in the let t go to infinity, the limit, right? There's a limit. T tend to 0, or just let t equal to 0, then you can have the value. So this is you need a two-step. Perform inverse Laplace transform, then plug in t equal to 0, then get the value. But now we can calculate just based on this. We do not need to perform this one. It is limit. Now s go to infinite. Here's a s times f of s. Oh, my example is not good. I put a 1. 1 is better. Okay. Then this is limit s go to infinite, s times 1 over s plus 3. Okay, what is this? This is 1, right? Because it's infinite over infinite. This 3 is nothing. Yeah, compared with infinite. So s over s plus 3, when s go to infinite, it's just 1. Alright. Yeah. So here you do not need to solve it. You do not need to solve it. Of course, this is just an example. Solve it is not hard. However, you can just calculate directly, right? Yeah. So this is the initial value. And similar, we can have the final value. The next one is the final value 0. Final value. Here we have a function f of t. We want to find the final value. That means t go to infinite. What is the value of this f of t? Okay. A similar thing. If we have the function in S domain, we have its Laplace transform. We do not know what is the signal. We only know this one. We do not know the signal itself. Then you can use this formula. It's still s times f of s, but now s tend to 0. S tend to 0. Okay. If s times f of s does not have poles on or to the right of the imaginary axis in the s plane, some condition. Okay, so you need to know what is a pole. Okay, let me explain this right now. What is a pole? Pole is like pole of f of s. If s over s times fs does not have pole. Now here I give the general. Okay, I use different letter. G of s. In generally, what is a pole of f of s? The value of S so that G of S, when S equal to that value, a value like I say is a pole, right? It's a P1. S equal to P1. When S equal to P1 equal to some K is a constant over 0. Constant. Like this. For example, that one, X of S equal to 1 over S plus 3, then S equal to -3 is a pole, right? If S is -3, -3 plus 3 over 1 equal to 1 over 0. 1 over 0. So this is a pole. This is a pole. Like another one, like Y of S is 1 over S squared plus 4 squared. Then S equal to 2J is a pole. You see, 1 over 2J squared plus 2 squared. It's plus 4, just 4. Plus 4 equal to 2J. J is a square root of -1. So square you get a -1. So this is a -2 squared is 4. -4 plus 4. Okay, you get 1 over 0. Yeah, when you have this one, something over 0, that is a pole. That is a pole. Because that is a point, you know, there's no value. You cannot assign a value on it. Right? This is a pole. I call it as a pole. And the related concept is a 0. 0 of G of S. The value I use 0, I say is a O1 of S, so that G of S, when S equal to that 0, this value is 0, just is 0. Like these two examples, we do not have pole, do not have 0, no 0, no matter what is S. The numerator is always 1, right? Then the whole thing cannot be 0. Maybe you can think S go to infinite, this is 0, but usually we do not use infinite as a value. Right? We can have some other value, other example. Like K of S equal to S times S plus 2, here's S plus 3, S plus 4, S squared minus 9. Yeah, this one we have 0, K has zeros, S equal to 0, S equal to -2. Okay? If you plug in S 0 and S equal to -2 here, then the whole thing is 0, right? And the poles, S equal to -3, S equal to -4, S equal to positive 3. Oh, here's another -3. Positive and -3 both make this 0. So we have poles. Actually, these they are same. They are same. You can say these two, S equal to 3 is a pole with multiple with other two. The other two. You should multiple poles. You can have more, like order 3 or 5, even higher order poles are 0. Yeah, like if I have a square here, then you have two zeros at z equal to -2, right? Things like that. Yeah. So this one here we want S times Fs does not have poles on or to the right of the imaginary axis in the S-plane. Okay, here we have a concept S-plane. What is S-plane? S-plane. S-plane. S are complex valued variable. So S can be like 1, 2, 3, -1, -2, -3. Okay, no problem. They are real numbers, and we can also have like 3.5, like complex number, real numbers, and 1 plus j, 2j, -4j, like -9.3 plus 4.9j, things like this. You know, they're complex numbers. Then we can have a graph to represent it. So we need because the two, right? You have real part, the complex part, imaginary part, j part. So we have the real part, and here's an imaginary part in the graph. Like 1 plus j, here's 1, here's j. This is 1 plus j. And the 2j, here's a 2j. And -4j, 1, 2, 3, 4, -4j. And -9.3, -9.3, and the positive 4.9j is this one. It's a -9.3 plus 4.9j. So every complex number or every value of S, it is located in a plane. You know, located in a plane. This is a plane. This is S plane. Yeah, it's two-dimensional, right? Two-dimensional. It's a plane. It's not a straight line. It's a plane. Yeah. All the complex numbers, because every complex number, it is the combine of two parts. Each part, first part is real number. Second part is a real number times j as a different unit. Yeah. Okay, so this is S-plane. S-plane. Just a plane. Yeah, it's a plane. It's a complex number. It's a plane. Yeah. Okay, then we go to next. Here is a kind of, this is a shift on S domain, right? This is capital F of S plus or minus alpha. So we have a shift on S plane, right? In this S plane, right? S plane, we have shift in the S plane, and then what happened in the time domain? It is this one times exponential power of negative alpha t or plus. Yeah, just minus is fine, or just plus is fine. Doesn't matter. Yeah. So here's a plus, here's a minus, here's a minus, here's a plus. Okay. This is a duality property of this one. You can see shift in time. We have these, right? Shift in time, then we times the exponential power in S domain. Now shift in S domain, we times the exponential power in the time domain. So these two properties, they are duality. But not exactly same, because in S domain we shift, just shift. We do not need times like a us of t here, right? We do not use this unit step here. Just f itself. We just shift it, it's fine. And in the time domain, we times exponential power. All right. And the last one is convolution. When we times two signal together in the S domain. In S domain, if we multiply these two together, then in time domain is this one. This is convolution. Like convolution, we use this star to denote the convolution. Actually, we have a duality feature. Didn't list it here, but we didn't use it in this course. You can know that if we have a convolution in time domain, then related in the S domain is a multiplication. Oh, it's just this one. This is a convolution in time domain. Here's a multiplication in S domain. And the reverse one is, if in time domain is a multiplication, it's just times, not a convolution, it's a times. Then in the S domain will be a convolution. Yeah, that one is well, we never use it. Yeah, this one maybe we use it somewhere. Okay. Okay, that's all I want to give you today. We have two tables, and I go over the table for you, and you should understand how to use it. That will be great. All right. Okay, see you next time. Bye bye. Yeah, it's the time.